Our objective is to identify a step that can be performed along a descent direction in order to generate a new iterate, which is good, which is better than the previous one. However, we have seen on simple example that just asking that the new iterate is better than the previous one may not work. So we need to characterize what a good step is, and this is what we will try to achieve in this video. Actually, we will need two conditions to characterize a good step. This video will focus on the first condition, and the next video will focus on the second condition. So the context is the same as before. We are minimizing a function f of n variable. We are currently at a iterate xk. We have calculated a direction dk, which is a descent direction, because the directional derivative is negative. And now we have seen that asking for a decrease is not sufficient. We have understood it because if you perform steps that are too long, well, it's not consistent anymore with Taylor's theorem, and anything can happen. There is absolutely no guarantee whatsoever. So the idea that we will do here is the following. Well, it makes sense to make long steps because we would like a fast algorithm. But then we will challenge the algorithm. We will say, okay, you are allowed to make long steps, but if it's really worth it. I mean, the example, if you remember that you have seen in the last video, we made relatively long steps and the decrease in the objective function was really tiny. And that's what we would like to avoid. The improvement that we perform on the objective function should somehow be consistent with the length of the step. If we make short steps, it's okay to make small decrease in the objective function. But if we make long steps, we want the decrease to be long, to be big. So that's why we express with this equation here. We say that the decrease of the objective function when we move from xk to the next iterate xk plus alpha k dk must be at least something which is proportional to the step length. So that if alpha k is small, we will allow a small decrease, but if alpha k is big, we will require a large increase in the function to consider the step to be acceptable. And gamma is the proportionality factor. Another way to write the same equation is to say that the new value of the objective function must be, of course, less or equal than the old value minus alpha k times gamma, which is the minimum reduction that we are expecting from this iteration. And gamma must be positive, of course. So that's the idea. Let's illustrate it on a simple example. So here I have a function which is reported here, and you have the plot of the function with the level curve. I'm currently at this iterate here, and now I'm looking into this direction here. It's a descent direction. What I have plotted on the right is the value of the function as a function of alpha along this direction. Okay, so the main line here is the value of the function. And now I have plotted the line which of equation f of xk minus alpha gamma, which is the line that is defining the condition that I have introduced in the previous slide. So basically, I would consider a step to be acceptable if the value of the function here is below this line. So for example, the value alpha equals 1 corresponds to a value of the function which is below the line, so this is considered acceptable. The decrease that I've made corresponds to a sufficient decrease in terms of the condition I have introduced. While if you look at alpha equals 4, the value of the function is above the line. So here, the decrease that you have obtained is not deemed sufficient. And as you can notice, the decrease is bigger than the one that we have achieved for alpha equals 1. But alpha equals 1 has been considered acceptable because the decrease was sufficient for a short step, alpha equals 1. Now, when we want to do alpha equals 4, it's a long step, we have more requirements. And this decrease that we achieve here is not deemed sufficient. Okay? So in this example, we can see that any alpha which is basically less or equal to 3 dot something will be acceptable according to our condition. So that's the idea. Okay? If you make a long step, you better decrease the value of the function significantly. And this is defined by this linear condition. But this value of gamma looks strange. Here I put gamma equals 6 just for the sake of the example. Well, obviously, this is arbitrary. So let's look at another example. Actually, I will take the same function and I will look into another direction. So same point, and I look in a different direction here. So I do the same plot. I have the value of the function as a function of alpha along this direction. And here, the plot of the line which is defining the condition. But in this case, the line is strictly below the value of the function for every alpha which is different than 0. Well, actually, the reason is that along this direction, dk, as you can see, the function is relatively flat. So we cannot be as demanding as before because here we are in front of a relatively flat direction. So the use of gamma equals 6 is not appropriate anymore. We should be more flexible and put a lower value of gamma. Actually, it's like when you are doing skiing. If you are in front of a very steep slope, you expect to go down very quickly using your ski. While if you are in a flat area, you are not expecting to lose altitudes very fast. And that's the second idea of our method. We would like to calculate the value of gamma that we put arbitrarily to 6 in the previous example to a value that accounts for the local slope. And what is the local slope? It's the directional derivative. So in the same condition that we had before, so a function f, a current iterate xk, and a descent direction dk, I would like to choose gamma, which defines the requirement for the decrease of the function, to depend on the directional derivative. But this directional derivative is negative, and gamma must be positive, so I need to put a minus sign. And then I would like to be more flexible and to have more choice for gamma. In particular, I will multiply it by a factor, which will be strictly between 0 and 1. Okay? So gamma will be proportional to the slope of the function along dk at the current iterate xk. And the proportionality factor is called beta 1, and it must be strictly between 0 and 1. We obtain the so-called first Wolff condition. So we start with this definition that we have presented as the first idea. That is, the new value of the function must be less or equal to the previous one minus something which is proportional to alpha. And the proportionality factor, based on the second idea that we have just derived, is equal to minus beta 1 times the directional derivative. So putting gamma into the first equation, we obtain this first Wolff condition. Let's understand now why we need beta 1 to be strictly between 0 and 1 by looking at the extreme cases, which actually are excluded. We don't want beta 1 to be equal to 0, and we don't want beta 1 to be equal to 1. So if we have beta 1 equals to 0, it means that the first Wolff condition is equivalent to asking that the value of the function at the new iterate is less or equal to the value of the function at the previous iterate. And this is not acceptable. First, we have seen that asking that it's strictly less is already not sufficient to converge. So we refer you to the previous video for an example. So a lesser or equal will not work either. And the value beta 1 equals 1 does not work either, because in this case, the equation here on the right is actually the equation of the tangent of f at points xk along dk. But if the function is convex, we know that the tangent is below the value of the function. And therefore, there is no alpha k that will be able to verify this condition. So let's illustrate now this Wolff condition on the example that we had before, and this example where the value gamma equals 6 didn't work. So we have again the flat function, which is represented here. I have represented the tangent here, okay? And as we have discussed before, the tangent, because the function is convex, is below the curve. So this tangent cannot be used as a condition. So that's why we need beta 1 to be less than 1. And here we have selected a beta which is close to 0. We have taken beta 1 equals 0.01. So we obtain, for the first Wolff condition, a line here which is almost horizontal. All values of alpha which are lower than 3.8 something will be considered as valid. It means that these values of alpha are associated with a sufficient decrease of the function, where this concept of sufficient decrease is characterized by the Wolff condition. Now we can do the same for a larger value of beta 1. So here we did exactly the same, but the value of beta 1 is closer to 1. So it means that the Wolff line here is closer to the tangent. It means that the set of alphas which are considered valid is way smaller. So there are only small steps that can be performed. So we see that when beta 1 is close to 0, we allow longer steps. When beta 1 is close to 1, we allow shorter steps. And actually the theory tells us that this method will work for any values of beta 1 strictly between 0 and 1. Therefore, for any practical purposes, it's better to take a value of beta 1 which is close to 0, because then the set of steps that are considered valid is larger. And therefore, a trial and error algorithm will have a way easier job to find it. In this video, we have derived a condition that characterizes steps that are associated with a sufficient decrease of the objective function. The concept of sufficient is associated with the slope of the function at the current iterate along decay. If the slope is big, we are expecting potentially a big decrease, and our requirement will be bigger. If the slope is small, it means that the function is flatter. We cannot expect such a big decrease, and our requirements will be lower. And then we have some room for maneuvers. We have this parameter beta 1, which must be strictly between 0 and 1 to characterize the level of requirement. If beta 1 is close to 0, the line that defines the condition is almost horizontal. So it will allow to make longer steps. If the value of beta is close to 1, the line is close to the tangent of the function, and therefore smaller steps will be acceptable.